If you watched the previous video in this series, then I tried to convince you that more or less everything that gets covered in a traditional Introduction to Statistics class is actually the same thing. It's just a slightly different flavor of a linear model, which is an extremely powerful and robust modeling framework that can produce models of a whole range of different scenarios where we are trying to predict a y variable x, and we have some combinations of different x variables to help us make that prediction. What sometimes happens, though, is when people get to the real world and they leave their statistics classes behind and they take a look at the actual data that they have to work with, they might see a curve which they don't know how that fits into a linear model. They might see some residual plots which clearly show some deviations from what they would like to see. You've got variability all over the place in slightly strange, non-standard ways. You're not sure if your points are independent. You're not even sure if a curve or a line makes sense at all for what you want to deal with. And this is the point where many people start to get stuck and start to look at what the next step is beyond linear models. And this is where there is no single next step. It really depends on what the objectives are, what the problems are with a linear model, if you've encountered any problems, and what questions it is that you want to ask. Nearly everything is just one step beyond a linear model, but that one step is going to be different for very different contexts. And so in this video, I'm going to try and troubleshoot some of those common scenarios that people run into of what should I do when I see that I have a particular characteristic or a particular problem that I would like to solve. And I'm going to go through a whole bunch of different modeling techniques and try to decode them as quickly as I can and give you some suggestions of when they might be appropriate to look at in your own work. So first up, what should we do if we have a trend which is not a straight line? We have some kind of curvature or something else going on in our relationship between our predictor variable x and our outcome variable y. The first thing to consider is whether it looks like a simple curve that you can explain and that you can parameterize by perhaps putting in a log transformation to create an exponential curve or a quadratic term to deal with a curve that goes up and then down again. And that can be applied through a linear modeling framework by adding in transformations of your existing variables. If you've got something a little bit more complicated than a simple transformation of a variable, a slightly more complicated looking curve, perhaps one that you already know because there's various scientific literature out there about the relationship between y and x, and you're trying to estimate particular parameters about that known distribution and that known relationship between y and x. There is a realm of statistical models called non-linear statistical models, which can deal with more complicated curved formulae. But often a better solution and a more robust solution, if there is no such known relationship, rather than trying to come up with a complicated formula to explain the curve, it could well be that the curvature you are seeing is because of an additional factor or a hidden covariate or a missing variable in your model, which would explain why it appears like the relationship between x and y follows a curve because of a third variable, z or x2, whatever you want to call it, which is causing that relationship between x and y to look like a curved relationship when you consider the variables one at a time. And you also have the option of thinking about a non-parameterized model, a smoothed model, like we see often if we put a smoothed line onto a scatter plot in R, for example. That will be doing a non-parametric curve through a generalized additive model or a low-S model. That has some drawbacks because this is based purely on the trends of the data. It's a very data-driven approach compared to something which is maybe more robust and more applicable outside of your data. But it could be a good option as well when it seems like your curve definitely doesn't seem to fit into any known formulae. And then another really common question is, what should I do if my response variable isn't actually a number, it's a categorical variable. And this is where the options are a little bit more straightforward if you have a binary variable compared to something which is taking more than two possible outcomes. So if you have a yes, no, 0, 1, presence, absence, true, false outcome variable, then this has a lot of very nice statistical properties, and there is a specific form of regression modeling known as logistic regression, which can deal with that. If there are more categories, then there are also alternatives to deal with this parametrically, such as multinomial regression or ordinal regression if it's an ordered categorical variable, but often a more non-parametric approach, dealing with more machine learning classification methods, could be just as powerful and perhaps often a little bit more robust than some of those parametric classification methods, which come with quite heavy sets of assumptions. So something which comes up all the time when people check their model and they try to see if those residual plots make sense and the assumptions for that linear model hold, and they'll see that the residuals are not spread evenly throughout the whole range of observed values. And this is where there's some methods where we could take transformations, particularly if we see very predictable shapes in those residual plots. So if we see something that looks like a funnel, then this is where we might be trying to take a log transformation of y, because what that's indicating is at lower values we have lower variability, at higher values we have higher variability. And that's a classic setup where a logarithmic transformation is going to adjust for that perfectly. If we've got the reverse shape and more variability at low values and then less variability at high values, that's possibly indicating that an inverse transformation, so 1 over y, might be a better way of trying to deal with that statistical model, because that will help explain that variability at the lower end a little bit better than if we look at y on its original scale. Another quite common pattern to see is a diamond, where you've got low variability at the lower and upper ends, and then higher variability in the middle. And that's usually the case when you've got something which perhaps has higher upper and lower limits and bounds to what values the y variable can take. And this is why at the extreme ends you have less variability, because it gets cut off if you can't have values below 0 or above 100, for example, because what you have is a score on an exam as your y response, for example, where everyone has to score at least 0 and they have to score less than 100%. And often that's actually the case when you perhaps have a binomial variable and you didn't realize you had a binomial variable. An exam score is a perfect case of that, because your exam score is actually made up of multiple binary events. You either got the point for a certain question or you didn't get the point for a certain question. And those binary events add up to a binomial distribution when you combine them together to make an exam score. And so this is where you again might think of logistic regression to deal with a case like this. And there are also censored regression methods which exist to deal with perhaps a case where you only have an upper or a lower bound for your particular variable. If it doesn't really fit with any of those patterns, then there's also methods like weighted least squares if the variability is a little bit less predictable, particularly if you're dealing with an x variable that is a grouping variable rather than a continuous variable. That may be a good approach to dealing with that. But at this point, you may have gone through and you still can't really come up with a curve or a line that fits your data particularly well. You still don't think you've been able to deal with the distribution of the residuals through some of those tips, or your problem is you think to do with the distribution of the residuals and you don't think you can get away with a normal distribution as the assumption for how those residuals are distributed. And this is a point where some of the methods I've already mentioned fall into this category, but we would want to move from a general linear model to a generalized linear model. And this is the point where we start thinking about what distribution should we be making an assumption around our variable following, rather than a general linear modeling framework where we go with the normal distribution. The obvious follow-up question is then always, I don't know what distribution to pick. And there's a few very common cases which are quite flexible to deal with. So if you have a count variable, an integer variable, the number of events, and particularly if those number of events is relatively low, that's when you would be looking at a Poisson regression model to deal with that integer outcome. I've already mentioned the binomial family, which links to a logistic regression model. These are one and the same thing. A binomial generalized linear model is another name for a logistic regression model. And you would deal with that for proportions or percentages or binary variables or probabilities or the number of events out of a total. All of those things are actually kind of the same thing, even if we think of them slightly differently when we talk about them. Other quite useful distributions to be aware of are the gamma distribution. So this is where you might have something which is very non-symmetrical, very skewed in one particular direction, or you have something which has a much longer tail and more extreme values than you would expect from a normal distribution. And this one comes up a lot in things like climate modeling, where you have often a slightly strange distribution of things like rainfall or temperature, where you do have those long tails for more extreme events being more common than you would expect under a normal distribution. And then the other very common problem that people realize when they're starting to think about those assumptions regarding the linear model is I don't have independent observations. I know that I have done a experiment where I specifically went to 10 different sites and then sampled within those 10 different sites. So I know there is some dependency linked to the site level. Or I know that I've got data every 5 minutes for a long period of time over months, and I know that my data now is very strongly auto-correlated to what the data was 5 minutes ago. And similar for spatial methods, I know the result of the soil sample I take here is going to be very similar to a soil sample I take a meter away from here. And the further away in time and the further away in space I become, the less dependent I am on the results from this particular location. And this is where we extend from the generalized linear model to a generalized linear mixed model. And this can deal with any of those three scenarios in slightly different ways of that hierarchical or clustered grouping, where we have multiple observations from the same group or the same unit. For example, if we take a before measurement, a during measurement, and an after measurement for some kind of treatment, that would fit into this framework as well as having something which was multiple samples from within the same location. And certain types of time series analysis and geospatial analysis can also be dealt with through that generalized linear mixed model framework, where we are able to partition the variance into multiple categories. But there are also specific methods which can deal with time series and spatial analysis in slightly different ways, which are specific to those contexts and perhaps make sense where we have a higher density of data compared to GLMM, which will work a little bit better where we have less frequent observations over time or over space. There's also that common scenario where you've been thinking a lot about your first model and then you realize that you actually have measured 10 possible response variables rather than just one response variable within your data set. And you kind of want to know how all of these different responses link together and what's going on with the overall picture rather than just having to deal with them one at a time. And there's no shortage of different multivariate analysis methods which can deal with slightly different questions that you might have about how those response variables link together, particularly whether you're trying to separate them out or group them together or see how a group of predictor variables can predict all of those Y responses all at once. And this is again a much bigger topic to explore more about for trying to tailor those towards your specific needs for multi-dimensional analysis. And then there's often the question where people will ask that they don't really care about how the variables are related to the outcome. They just know that they are, and they would like to try to work out the best possible combination of those variables to make a prediction for the outcome variable. And this is where we get into the world of predictive modeling rather than inferential modeling, where we're looking to maximize the predictive quality rather than try and build a model that we can explain and that we might be able to link to scientific theory in the same way that we can with some of the classic statistical methods. And this is taken off quite a lot in recent years with improvements in computer processing speed and the ability for anyone on any kind of basic computer to now be able to run very powerful machine learning and artificial intelligence algorithms. So if you know that your focus is going to be on predictive modeling rather than inferential modeling, there are many different techniques out there and many different specific considerations that you would need to be thinking about if you're going down that route. Particularly thinking about whether there may be biases in how the data was collected and the sampling methods for how the data was obtained, and whether those would be generalizable when you're trying to think about predictions beyond the data set, the concept of external validity, and then also the internal validity of some of those models, where if you don't treat it very carefully and make sure that you are accounting for issues around overfitting, some of these models can quite easily start to find trends which will be very, very specific to the data that you have trained them on, and then won't hold up if you test them on some independent data sets. So partitioning your data and doing cross-validation is very important when you're dealing with this machine learning approach towards statistical modeling. And then there's a different question, which is, how does what I have in my data link to what we already knew about the relationship that we're trying to study? And this is where, in many cases, there could be some pretty established scientific literature out there about the relationship that you're trying to model. What you are doing is not necessarily unique. You may be applying it in a slightly different context, or you may be looking at something which is in a different environment to which it's previously been studied, but you're not coming in with no information and a complete blank slate about the relationship between X and Y. And this is where Bayesian methods can combine what we already know or what we think we know about the relationship with what we have in our data. And we can set that level of knowledge and that level of evidence that we have prior to our data in different ways. We can have what we call strong priors, where we think we have very good knowledge already about what it is that that relationship should look like, and our data would need to have very strong evidence to be able to challenge those priors and to get us to update our underlying working theory for that model. And then on the other end, we may come in with very weak priors or even non-informative priors, where our data is going to be the main driving force in driving what it is that we have as our final model of this particular relationship. And this is where we combine our data and our prior distributions around each of the parameters with different weights depending on the strength of evidence from each of those two sources to give us what we call a posterior distribution and a posterior model. And even if we have non-informative priors, we'll end up with a model through the Bayesian framework which is more or less functionally identical to the frequentist framework, which is how we refer to classic statistical methods. But the way in which we can interrogate it and make inferences from it is a little bit different, because there's a few different angles that we can explore, particularly because we stop considering those model parameters to be fixed concepts that we're trying to estimate. In a Bayesian framework, we now consider the beta naught and the beta 1 to themselves have underlying distributions and to be themselves variables rather than fixed concepts that we're trying to estimate. And I could keep on going with more different explanations and more different scenarios, but even by this point in the video, I've covered quite a lot of different methods, and you may be thinking it's going to take me a long time to start to unravel all of those different methodologies which we've discussed as being one step beyond the linear model. But there's a few very important things here which make that job a little bit easier than it seems, because all of the methods which I've talked about do have a very strong link back to the general linear model. This is almost the starting point from which nearly all of those methods are built. And the way in which you think about them is extremely similar, even when the formulae themselves start to get more complicated. A simple general linear model, if you wanted to calculate that by hand, and you may have had to do this in particular undergraduate courses, you could calculate that by hand. When you're getting to mixed models and Bayesian models, only a computer would be able to deal with that. But what we need to focus on is less the complexities of the formula and more the commonalities of what those models are telling us and how we can interpret them and under what assumptions we need them to be valid. The analogy that I often give is that you do not need to be a mechanic to be able to drive a car. It's useful to know, and it's good that we have mechanics out there who are able to fix the engines and be able to improve the ability of cars to function in the modern world and make them increasingly efficient and whatever they need to be done. In the same way that it's good that we have people working in statistical methodology to develop new models and to improve existing models. But for the majority of researchers who are going to be trying to do the best possible job of analyzing their data and coming up with a model that best explains the phenomenon that they're trying to study, this is where the focus really needs to be on what the model is telling us and whether the model is valid, more so than all of those complicated pages of formulae that you can find if you search for some of these models online. And this is where, if we are using a statistical software tool like R, that really encourages that way of thinking. Because the way in which we change between all of the different methods that we've covered here is a way which really emphasizes that common DNA. The function looks almost identical for all of those different methodologies, except you change the name of the function, you might add in a few options. Fundamentally, the code that you write looks very, very similar, and the output from that code looks very, very similar. To try to make it as easy as possible, once you've got the hang of interpreting a model in a particular way, you just need to know the slight modifications for your new model to try to be able to best understand and interpret and assess the quality of those models.